Okay, so we're going to talk about sets. A set is a well-defined collection of objects, and it may or may not contain numbers. And we're going to be talking about many sets that do contain numbers, like the real numbers, which includes the natural numbers, integers, and rational numbers. And later on in the book, we'll also talk about complex numbers. So a set, an example of a set would be set P, and I'd write it with a capital letter P, and I write set P is equal to, and then I'm going to list some numbers that are in that set: 1, 3, 5, and 8. So there's my set P. And sometimes it's useful to refer to the objects that are in that set or not in that set, as the case may be. So I may want to say 3 is an element of set P. And this little notation here, this is a Greek letter epsilon, lowercase. It looks like our E, kind of, and it is red, is an element of set P. And sometimes I want to say that an object is not in this set. And in this case, I notice that the number 2 is missing from set P. So I may want to say 2 is not an element. So this says 2 is an element, and I put a line through it which shows that 2 is not. Actually, I don't like the way that looks. So let's try this again. So 2 is not an element of set P. And that just means 2 is not in that set. And so we'll write is not an element of set P. And you may say, well, that's kind of stupid, because I can look at P and there it is. I can see clearly 3 is there and 2 is not there. Why would I ever want to use that notation? Well, not all sets are, this P only contains 4 elements in there. It's got the 1, 3, 5, and 8. Not all sets are that small. This set, because I can list all the things that are in that set, has a descriptor that we call it a finite set, because I can list all the members in that set. But there are other sets that are also finite that are much larger than that. For example, maybe I'm looking at the set of numbers from 1 to 100. So I can list them all if I wanted to take the time, but I'm just too lazy and I've got better things to do. So I'm going to list 1, 2, 3, and I'm going to go all the way up to 100, but I don't want to write all those numbers, so I use 3 dots, dot, 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 and then a comma, and then 100. And what those 3 dots show is that pattern that we can see over here, just going up by 1, continues until we get to the end number of 100. But it's still finite. If I took the time, I could list all those elements out. And in this case, it may be quite useful to say, well, I may want to refer to 5 is an element of P, because I don't see it there. And maybe it's not obvious to somebody. So those are finite sets that you can list. Well, there's also the case where you have an infinite set. So an infinite set is a set where you cannot list all the members. And an example of an infinite set would be the natural numbers. So maybe I want the set n of natural numbers, which is the set 1, 2, 3, and so on. But there's no n number. It doesn't stop at 100. It keeps going forever. And the way we show that is we just put a closing bracket here with no n number. And again, I may want to use this notation and say, okay, the number 100 is an element of n, the natural numbers. Okay, so we're going to continue on with sets, and we were talking about sets. One way to define a set was to list everything in that set, but that's not the only way. Sometimes we can use a description, and we might write something like this. The set W, which equals the set of all x such that x is a car. Okay? So that would be the set of all cars. Or we might write the set of natural numbers that we talked about before as n equals the set of all numbers such that x is a natural number. And there's my verbal description of it in my bracket. And there's also two other sets, and they seem kind of strange sometimes to people when they first study math, but they're important to have. And actually, it's one other set in two notations. It's called the empty set. And the empty set is just what it says. It's the set with no elements. It's empty. And you used to see this set just written like this with empty brackets. Now more commonly, I think you write it like this. And that means it's the empty set. Okay, so we're going to go through a couple examples. I'm going to call this example 1 so that it kind of matches what's in your book. And the instructions say, write the following sets in two ways. So the first one will say the set P containing the natural numbers less than 5. So one way I could do that is I could say P, and I could list all the natural numbers that are less than 5. Now the natural numbers start at 1 because, believe it or not, people didn't think of the number 0 for a long, long time. We started counting with 1, and so those are the natural numbers. And so 1, and then we go to 2 and 3 and 4, and then we stop because it says less than 5. So those are the natural numbers that are less than 5. So that's one way, is listing them out. Another way would be to say the set P, and then we can use a mathematical descriptor. P is the set such that of all x such that x is a natural number, and we can use that capital N. It's in mathematical circles, it's known as the natural numbers. And the set of all x such that x is a natural number, and then comma, and we're going to say and x is less than 5, and then our curly bracket. So those are the two ways we could write that set. Now, for a second example, maybe we have the set W containing the natural numbers that are at least 10. So W, could list that out. It'd be 10. Could be 10 because it's at least 10 or more. So 10, 11, 12. Now this first set that we looked at is a finite set. So I could list them all. The set we're doing right now is infinite because I can go on forever. So I'm just going to use our little technique of dot, 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 and there's our set of natural numbers that are at least 10. And of course we can write that in mathematical descriptors by saying, well, W is the set of all x such that x is a natural number and x is greater than or equal to 10. And there's our description. And we've followed the directions. We've written the sets in two ways. We did a listing and we did a descriptor in mathematical notation. Okay, so next I want to talk about the relations between sets. So sometimes sets are equal. So I could say x and y are equal. And we define them as equal if they have exactly the same elements. And that seems to be, makes sense. I don't think there's anything that's hard about that. If they have exactly the same elements in both sets, they're equal. And then the second part of that, this is a little bit more interesting, I think, is A is called a subset of B if each element in A is also an element of B. And we use this notation, A and sort of a sideways U with a line underneath. A is a subset of B. And what that means actually is A could be equal to B. That's what that line is. But it at least every element in A is also in B. Maybe all of them are, and it's equal. So that's what the line is. So if A was a smaller subset of B, which we knew did not contain all the elements, we might write it like this. A is a subset, but not equal to B. And here it could be equal to the first one. So here with this line, it could be equal to this one. It's strictly smaller than B. And there's one final thing, and it's if two sets have no elements in common, we use the word disjoint. Okay, so that's if two sets are totally they have no elements that are in both of the sets. They're called disjoint. All right, so example 2. And we have a few sets. We have the set M. It's the set of all x such that x is less than or equal to 5, and x is a natural number. And instead of writing all that out, let's write it like this. X is an element of n, the natural numbers. That's the purpose really of some of that mathematical notation, is to make it easier for you to show things with less effort. And so we have that set, and then maybe we have the set W. It's going to be the set 2 and 4, and maybe P will be the set 2, 3, and 11. So I've got 3 sets there, and I could ask the question, which of the sets are subsets of M? Okay, so M is the set of all natural numbers that are less than or equal to 5, and W is the set that contains 2 and 4, and P is the set that contains 2, 3, and 11. So which sets are subsets of M? Well, a subset means every element of the first set is an element of the second set. And we can see that W, 2 is a natural number less than 5, and 4 is also. So W is a subset of M. Okay? We could write it like this, it's strictly smaller, or you could write it like this, which means it's less than or equal to, but we can clearly see it's not equal to. P is not a subset because it contains, 2 is in M, and 3 is also in M, but 11 is not less than 5, so P is not a subset, so we cannot say that it is. We might ask the question, so this was the subsets. Okay. We might ask the question, which ones are disjoint? Okay. And none of them are disjoint, because if I look, both sets P and W contain 2. Okay, so they have a common element, and in fact all 3 sets contain the number 2. So if there was one set that did not have an element, or 2 sets that did not share any elements, they would be disjoint. So in this case, none are disjoint. And then the last part, it says, C, are any of the sets equal? So do any of the sets have exactly the same elements in them? And the answer is none of them, because they all each set has an element that the other 2 do not. So we're going to talk about real numbers for a minute. Real numbers are the most common numbers that are used in the world, and so the most important numbers to talk about in this text. There's 2 types of real numbers. Oops, I spell it with an E, not an A there. So real numbers, they can be classified as either rational or irrational. And rational means that you can represent that number as a fraction. Okay? So what numbers are rational? They include integers, fractions containing only integers with no 0 in a denominator. So fractions, as long as there's no 0 in the denominator, because that would be undefined. And decimals that either terminate or repeat. So all decimals that terminate or repeat. Okay. So what do those numbers look like? So some examples might be -7, square root of 4, which is 2, of course 0, maybe the number 11, -2/3, 6.58, and how about something like this, 0.33 repeating. Now, irrational numbers, there's one that's really well known all the way from middle school, and that's the number pi. Okay, the ratio of a circle's circumference to its diameter, and so pi is a irrational number. But also any radical of a number that's well, I guess the most common one is any square root of a number that's not a perfect square. So, for example, the square root of 2. And we can compare that to the square root of 4. Square root of 4 has a 4 is a perfect square, so it has a whole number answer, 2. But numbers like the square root of 2 do not. 2 is not a perfect square, so that answer will be irrational, and that goes for anything. And the square root of any other non-perfect square. Square root of 5, square root of 11. We could go on all day like that. But it's also true for other roots, like the cube root of 7, okay, or the cube root of 11. So there's no number that times itself 3 times gives you 11. No whole number. And because of that, well, not because of that, but that is an indicator that this is an irrational number. And if you plug this in your calculator, what you'll get is a long decimal number, and it never ends, and it never repeats. Okay, so we've used inequalities in our math career, and these are statements such as A is less than B, meaning that A is to the left of B on the number line, or we might have A is greater than or equal to B, meaning A is to the right or at the same spot as B on the number line. So on a graph it would look like this. So we'd have, when we say A is less than B, here's B, and A is going to be somewhere down here. A is less than B. And then if we say A is greater than or equal to B, so here's B, it might be at B or to the right of B. Well, we can represent this same information by using something called an interval notation. So if we have B here, it cannot be equal to B, so we would use a rounded parenthesis, and we would write B, and then we put a comma, and this goes all the way down to negative infinity to the left, and so we'd write negative, we use the symbol infinity, which looks like a sideways 8. Now that negative infinity, it's not a number. It's just it's a symbol that represents the idea that it goes forever to the left. So this is going continuously to the left, and it never stops. So similarly for this one, we're going to A is greater than or equal to B, but in this case it could be equal to B. And so instead of using this rounded bracket here, because this one was not equal to B, it was just less than B. When it's equal to, we use a squared bracket, and so it doesn't take long to get used to that at all. So this shows that A is greater than or equal to B. So A is to the right of B, but it could be equal to B. So here's B in the square bracket, comma, and again it goes forever to the right. So in this case it's going to be positive, and it's going to be positive infinity. And we always enclose the infinity side with a rounded bracket because it goes forever and never stops. So you can't encapsulate. You can't actually be equal to infinity. It just goes forever. So we never put a square bracket, with the infinity symbol. It's always around it. All right. So sometimes we also have a representation like this where we say, some number x is between A and B. Okay. So it's to the right. X is to the right of A and to the left of B. X is between A and B. And you could represent, so here's A, here is B. X is in between but not equal to either one of them. So it's not equal to A, and it's not equal to B. So we're going to use rounded brackets, and we put A, comma, B. So it's the interval between A and B, but not equal to them. Now if I change that and I did a is less than or equal to x, less than or equal to b, the only thing that changes here would be that I would have a, if I was graphing it, I'd have the solid dots at a and b, and instead of a rounded bracket, I would have a square bracket to show that it could be equal to a and b. Okay, so example 3. So this might be so similar to what is similar to what you have in your book assignments. So we're writing the interval corresponding to each of the, write the interval for each inequality, then graph. So we might have something like this. So a might be -2 is less than x, which is less than 3. So first thing we look at is that this can be equal to, so that's going to be a squared bracket. This one is not equal to, so it's going to be a rounded bracket. So I know that it's going to look something like this. I will have a square bracket on the left side and a rounded one on the right, and then I have my comma, and on this side I have -2, and this side I have 3. I don't know why I like that so much better than inequalities, but I do. And so to graph this, so we have our number line, so we have -2, and we have 3, and on this end, down here on the left, it's going to be a solid dot, and this one would be the open, and this is the section of the number line we're talking about. So one more example, maybe we have x is greater than, oops, I don't know what I did. X is greater than 10. So this time it's not between two numbers, but it's just strictly greater than 10. So I look at the sign, it's greater than, so I'm going to use a rounded bracket, but it's going to continue forever, so x is to the right of 10, so I'm going to have a rounded bracket on the left, which with 10, and then it goes to the right forever. It keeps going, gets bigger than 10, and goes. So that's going to be positive infinity, and that'll be a rounded bracket. So you'd graph that like this. Here's 10, open dot, because it can't be equal to 10, and then you have your arrow going towards positive infinity. So where is infinity on the number line? It's the direction the arrow's going. It's somewhere up here. Okay, so algebraic expressions. Are combinations of variables which are represented by letters and numbers. Sometimes a letter can also represent a constant, and sometimes that can be confusing if it's not defined clearly to somebody that's reading somebody else's work. But for the most part, in what you're going to be working with, letters are variables, and algebraic expressions are a combination of variables and numbers. So examples of an algebraic expression might be something like this. It might be 2w plus 5y. So we have 2 multiplied by some number which we don't know, represented by the letter w, variable w, plus 5 multiplied by some variable y, some quantity that varies, and we represent it with this expression. An expression does not have an equal sign. So you can see there's no equation there, there's no equals. This is just an expression. Sometimes they look a little more complicated. You might have 2x plus 3 divided by 1 plus y. And so there we have a fraction with variables on the top and the bottom. Might have something more simple, that's just something like 3x plus 1. Okay. So there's a couple vocabulary words we should point to, and the one is the word term. The terms are separated by addition and or subtraction signs. So this first expression that we have has two terms. So we have the 2w and then the plus sign, which separates the second term, which is 5y. So it has two terms. This expression also has two terms. This whole expression just has one term. This one right here in the middle, because it's as a whole expression, it doesn't have any separation by plus or minus. If I looked at just the top or just the bottom, the top part of it has two terms, the 2x and the 3, and the bottom of the fraction, the 1 plus y, that has two terms. But as a whole expression, it only has one term. And then we also need to look at so if I look at this 5y here, we already identified y as the variable. But 5 also has a name. It's called the coefficient. 2f's. Okay. And sometimes there's a term without a variable, like we see in this and expression, where I have 3x plus 1. So if I just look at this one, so we have a coefficient of 3 here, a variable of x, and then this constant term of 1. So it's called a constant because it doesn't change or vary. It's 1 and always 1. Polynomials. Polynomials are algebraic expressions that have a finite number of additions and subtractions and multiplications of constants, and they have non-negative integer powers. So non-negative integer powers means that you can have fractional powers. You can't have variables in the denominator, or you can't have variables inside a radical sign. So examples of polynomials would be things like 2x minus 3y, or you might have 5x to the 4th power minus 2y. So those are polynomials. But when you have things that look like fractions, when you have fractions with variables in the denominator, you know it's not a polynomial. So if I have 2x plus 1 divided by 1 plus x, that is not a polynomial, because you're not allowed to have variables in the denominator of polynomials. And also, if I have a radical sign with a variable in it, like 2x squared minus 3 times the square root of x, because this x is in a radical sign, this is also not a polynomial. So the general form for a polynomial, we write it like this: a sub n x to the n plus a n minus, so sub n minus 1 x to the n minus 1 plus dot 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 plus a1 x to the 1 plus a naught. And we use this funny, it might seem strange and take you a while to get used to it, but we use this a sub n minus 1, and so on, just to show that these are the coefficients of this polynomial. These are not variables. They are some kind of constants, but we don't know exactly what they are at this time. And the x is the variable, and the power n and n minus 1 and so forth, those also have determined values, but again, we don't know what they are right now, so we just represent them as n minus 1 and so on. So this is the general form of a polynomial. And it may look crazy and when the first couple times you see it, but once you start working with it, it really and understand the parts of it, it really doesn't blow your mind. It's pretty straightforward. So we have a couple of vocabulary terms that go with polynomials. So one is called the leading term. That's the term with the highest power of x, or whatever variable that it's using. So that's the leading term. And then there's the leading coefficient, which is just the coefficient of the variable that's on that first term, and the degree of the polynomial. And that's the largest power of the polynomial, of the variable of the polynomial. So for example, if I have 6x to the fifth plus 2x squared plus 1. Okay, and usually when you write a polynomial, you usually write from the highest power. It's standard form, but you write from the highest power on down. So here we go from 5, then the next highest is 2, and then the constant term comes last, the 1. So if I look at this, 6x to the fifth is the leading term. It's the first term with the highest power. The leading coefficient is going to be 6, because that's the coefficient that's on here. And the degree of the polynomial, you can see that the highest power there is on that leading coefficient is 5. So this is a polynomial of degree 5. The leading term is 6x to the fifth. The leading coefficient is 6. So what we want to make clear is that the polynomial has to be in standard form from the highest power and then going down to finally the constant term before you talk about the leading term, the leading coefficient, or when you determine the degree of the polynomial. So here's a couple examples. This will be example 4. So I might have this polynomial, 3x squared minus 5x plus 2x to the fifth minus 1. And I might want to determine the things we just found out, the constant term, the leading coefficient, the leading term, and the degree. So what I need to do is rewrite this so that the highest power comes first. So my highest power is 2x to the fifth, and then the next highest power is 3x squared, and then the next power of x is x to the 1 minus 5x, and then subtract 1. So now I have it in order of decreasing powers of x, and I can identify this. The constant term is negative 1, so that's this right here, this part right here. And then the leading coefficient is well, the leading term, I should do that first. So I have 2x to the fifth. So let's do that in blue to be consistent. Need a bigger eraser here. So 2x to the fifth, the leading coefficient would be 2. And so, and my degree is going to be 5 because that's the power on the leading term. So we're going to talk about like terms. We can combine, add or subtract terms that have the same variables, exactly the same exponents. Okay, they're called like terms, and they're important because they help us simplify. So if I have something like this, 4x plus 5y minus 2x plus 3y, I don't want to leave it like that. I want to make it simpler, and I take 4x to the 1 minus 2x to the 1. So 4x minus 2x gives me 2x, and 5y plus 3y it gives me 8y. And so I can combine those. And then, of course, it can be more complicated sometimes. We can have combined powers. So if I look at this example, maybe like 2x squared y plus 4xy squared minus 5xy. If I look at that, some people have the inclination to combine the 2x squared y and the 4xy squared. But if they have the same variables, x and y, but the powers of each of them are not the same. I have x to the second power, and here I have x to the second power here. This only has x to the first power. So it's not the same powers on the variables, even though they both have an x and a y. And of course, this x and y only are to the first power. So none of them are like terms, and you can't simplify that at all. Okay, the last thing we want to talk about are subscripts and with variables. So your book talks about in a coordinate system, x, y. So here's our y-axis, here's the x-axis. If I have the point 2, 3, I would go over 2 and up 3. So this would be 2, and I go up to 3 and make my point. There's my point 2, 3. But sometimes I want to refer to generic points, and I don't, some point x, y. Okay, and so I'd put it here, and here's my. This would mean that this would be x, and this would be my y. Now, in this case, I clearly know that because it's over in this first quadrant, quadrant 1, that both x and y would be positive, because every x and y is positive there. If I had it in this quadrant, I would know that y would be positive, but x would be negative in quadrant 2. And then down here in quadrant 3, they would both be negative. X is negative, and y would be negative. And finally, in quadrant 4, x is positive, but y would be negative. Okay, so continuing with our subscripts, so if this is my y-axis, this is my x-axis, you might want to talk about two different points that are in your coordinate plane, but you may not want to specify exactly, you might want to talk about them in general terms, not about exactly where they are. And so, in this case, I might want to talk about x2, y2, and x1, y1. And so maybe, one place you might use this, if maybe I'm determining the slope of, that's a terrible line, huh? The slope of that line, if it was straight like a line should be. And so in that case, this would be the x1, and this would be the y1, and here I'd have the x2, and this would be the y2. And so you can see that when I'm looking at my slope triangle here, this is the quantity, this delta y, is the vertical distance here would be y2 minus y1, and the horizontal distance is the difference of the x's, x2 minus x1. And so that's where this becomes useful, because you just want to talk about x and y's, but clearly this x1 and this x2 are not the same x, and this y2 and this y1 are not the same y. So we use subscripts to distinguish between them. And you could make as many as you want. Maybe this is x3, y3. So enjoy yourself. Make some more points.